Welcome everyone on the second day of Life and Space Days organized by Polish Astrobiological Society, the open event dedicated to popularization of the knowledge about astrobiology and all the topics that are around of this space biology theme. My name is Dagmara Stasiowska and I'm representing Polish Astrobiological Society here today. And today with me I have a great pleasure to host Christiane Hahn, the lead for biology team in the European Space Agency, lead for biology within the Human and Robotic Exploration Directorate. And Christian today will tell us something about, of course, European Space Agency's program and how biology is incorporated in that program and how it can help develop the agency further, and maybe even how we can try to support this exploration topics. Christian has a PhD in neuroscience from King's College London. She also earned the MREs in developmental neurobiology from the King's College and Masters in Biological Research from Royal Holloway, University of London. And from 2019, as mentioned, she works for European Space Agency. So I think this is the moment I can give the floor to Christian and enjoy her speech.
Thank you very much for the introduction. I'm very excited to be here today and share with you some of the work we are doing in the Human and Robotic Exploration Directorate at the European Space Agency. I will start my presentation. So today I will give you an overview of what we do in the directorate and in general what opportunities are out there for researchers who want to make use of the platforms we have available in space and on ground. But before I start, a little bit about what we're doing at ESA in the Exploration Directorate. So we have the Explore 2040 strategy, which was recently developed, and this is what we are working towards, where the key objectives are to maintain a human presence in low Earth orbit, or LEO, to allow Europeans to explore the moon in the 2030s, and to prepare taking Europeans to explore Mars in the end 2040s. And all of the scientific activities that we are doing currently are, the aim is to reach those objectives.
Christian, sorry
as part of that, we have what is called exploration science, where we are using our various platforms and destinations. So we have facilities on Earth and suborbital platforms. We have low Earth orbit, or LEO, the moon and the lunar orbit, as well as Mars and the Martian orbit. And exploration science focuses on those destinations.
Sorry to interrupt you,
we
Christian.
have separated out different research streams into different categories. So for exploration-focused science, this is science that we want to do that will enable us
Christian,
to go to the moon and Mars. So it's really agency-driven science that we absolutely need. And here we have four categories in which the science
Christian,
fits
into. Are you able to hear me? Sorry to interrupt you, but we need you to ask you to put the full screen mode of the presentation because it was not visible for the audience. Sorry.
Oh, apologies.
Yeah, no problem. Just put the full screen mode because it's in the presentation mode for now.
Does this work better?
If you could use the presentation mode, so the button on the upper part of the presentation, I think that would work the best.
So this one you don't see.
Yeah, this is not changing along with your talk. So I think the presenter's mode would be the best. So this is the button in the upper part of the orange bar.
How about this one? So,
Still not the best, I would say. But if it's the best that we can do, then I think we will go with it. Just let's maybe try to change the slide so I can check if that works correctly.
um,
So I think we can go with that. Thank you.
okay,
Sorry for the interruption.
then I will just click through the slides. I apologize about that. Okay, I I apologize, but you should still be able to see the presentation. Um, so as I was saying, in the exploration focused science, we have four categories in which the science fits into. And these are local resources, environments and effects, crew health and performance, and habitation. So these are the themes in which the agency drives the research. But we also have exploration-enabled science. And this is science that is curiosity-driven and opportunistic. So making use of the platforms that we have available to perform fundamental science or applied earth science. And just a little bit about the different categories. I hope you can see it big enough. So in terms of the local resources, we are trying to map the resources on the different destinations that we have, so Moon and Mars. And the key outputs that we want to obtain are resource maps, resource models, and develop a handbook for material properties. In terms of environments and effects, we really want to understand the space environment and the effects it has both on the Moon and the Mars and in Leo, but also understand the effects it has on, for example, biological systems or the human physiology. In terms of crew health and performance, here we really want to investigate physiological adaptations of humans to the space environment, whether that's in low Earth orbit, on the Moon or on Mars, or a transit to Mars. And the key important point here is that we want to be able to ensure that we can send humans safely into these faraway destinations by understanding all of the risks and developing the appropriate countermeasures for those. In terms of habitation, here we are trying to research the kind of habitats that are important to keep the crew safe and that will get us to our destinations. So, for example, the production of food for a Mars transit vehicle, or just a safe and comfortable environment for the crew to live in for a long time. And here the key science outputs would again be a human risk rating report. So understanding what is the risk of being in such an environment for a prolonged period of time and the impact of radiation on this environment. And then we have enabled science, which, as I mentioned before, is the fundamental science that we can do making use of the platforms and the vehicles we are building at these different destinations. So, as I mentioned before, our destinations are low Earth orbit, the Moon, and the Mars. And we are building infrastructure to be able to have access to these so that we can do agency-driven research and opportunistic fundamental research. And I just wanted to highlight a few research highlights from the International Space Station, which is the destination we probably know about the most currently. In terms of biology, there have been a few projects that have really advanced our knowledge about the impacts of space and what we can do there. So, for example, there was a project called Suture in Space, led by Monica Munici's lab, where they were studying the impact of microgravity on wound healing properties. And they are preparing a publication on this, and if I can summarize unofficially, they found that there are some extracellular matrix proteins that are impacted by the microgravity environment, which is actually slowing down the wound healing process, which is a key information for us to know if we want to send humans into deep space destinations, because we might need a countermeasure to ensure that in case there's an injury, we can appropriately treat it. Then in a kind of different topic, there was a project called BioRock, which was led by Charles Coquel's group, where they were investigating bioleaching properties of some bacteria. And they were actually able to extract rare earth elements, which were brought with them to the ISS, kind of demonstrating a proof of concept that it is possible to use the space environment to perform bioleaching with bacteria that we bring from Earth. And then we have research into habitation type research streams. So there was a project called Biofilms, which looked at different antimicrobial properties when you laser structure metal surfaces. And this study will provide us key information about how we should be building our transit vehicles to ensure that there is not a lot of contamination around that could impact the safety of the crew. And for human health, for example, we are trying to develop tools that allow us to monitor crew health without having to perform invasive procedures. And here is an example of a project called Myotones, which is monitoring the biochemical properties of muscle using a device without having to take biopsies. There, I also wanted to point out that there are some Polish projects also that have flown to the International Space Station on Axiom 4, together with the Polish astronaut, Slavoj. So there were 4 projects that recently completed their flight. These are wireless acoustics, MXene in low Earth orbit, the stability of drugs, and Leopard ISS. These are Polish projects, also developed by Polish industry in some cases. And I just wanted to highlight that we are working across Europe with scientists from all the different member states of ESA and flying their research. In the future, since we are also targeting Mars, there was a strategic move to readjust the Mars sample return Earth return orbiter. So there was originally going to be a mission to Mars that would receive samples from a NASA payload from the Martian surface, and ESA would be building a vehicle to bring those samples back to Earth. Due to some political reasons, that is not happening. However, we want to redirect the Earth return orbiter, that was always our responsibility, to become a Mars orbit mission. And there are some opportunities for scientists to make use of that vehicle to perform some research. However, I just want to point out that we've just had a ministerial where the budget for the next 3 years is defined for our program. So we are still discussing which activities we are doing or not. So it's not yet guaranteed that this mission called Zephyr will happen or not. But I just wanted to point it out also because there are some Polish industry which will be building one of the 4 core payloads that would be transported on this vehicle, and this is a sub-millimeter sounder developed by a Polish company. I also wanted to highlight that the research that we do in space is not just to enable humans to explore space, but it also has practical benefits on Earth. So I mentioned already this project Suture in Space, which investigated wound healing in the microgravity environment. However, it uncovered some processes that were masked by the 1G environment on Earth, and this could also facilitate clinical applications on Earth on how to improve the wound healing process. Similarly, there is an eye tracking device that was developed for the ISS some years ago, because there was a research team wanting to investigate some cognitive functions, and the astronauts needed to look at a screen and their eye movements were being tracked, but they didn't want the laser from the tracker to interfere with the visual capabilities of the astronauts. So they developed a specialized laser. And this eye tracking device is now being used on Earth for routine laser eye surgery to enable doctors or operators to monitor the eyes without having it interfere with what they're doing. So it's really a direct link from something that was developed for space that is now being routinely used on Earth. And then I wanted to highlight also a study on bone remodeling called in vitro bone, where the science teams were trying to understand the impact of microgravity on bone remodeling. And there they have discovered a biomarker called irisin, which is linked to osteoclastogenesis. So this is when bones break down, and when there is more irisin, then there is also more osteoclastogenesis. And the research teams are now working on clinical studies to try and manipulate or synthesize an irisin version that would help treat osteoporosis patients on Earth. So again, it's a practical benefit for Earth that we have discovered due to being able to use space. And on to some practical things. I just wanted to mention as well how it's not very easy actually to send a life science experiment to the ISS or to any space platform, because ideally when you do your research, you want to be able to use the whole lab as you would in your laboratory. However, we cannot just transport a whole lab to space. There are some challenges. So for the ISS, for example, it takes around 5 to 7 days for the vehicle to reach the ISS upon launch. So when you have your experiment integrated into its hardware, it needs to survive for 5 days before it can be placed in an incubator, for example. And usually during that time, there is limited temperature control and also no exchange of liquids. So really, the scientists who work in the space domain have to adjust quite heavily their protocols that they would normally use in the laboratory to ensure that their samples make it alive to the destination that they want to reach. And normally, you can maybe see in the picture here, we have specialized hardware that is built to host biological samples that you would have in your lab. And you can see it's quite different from your standard well plate that you might use in the laboratory. And basically, there are industries who can build this kind of hardware. And once they have built it, it needs to fit into some kind of hosting facility. So in the International Space Station, for example, we have a biolab, which is basically an advanced incubator, which has a possibility for humidity control, temperature control, and it has a centrifuge. But it has very specific requirements with what can fit into it. So the industry building a hardware for the science teams needs to also know exactly what those requirements are and adjust to those and ensure that you can still perform the science you want to inside of this facility. And then once the experiment is done, normally we would use cold stowage to transport the samples back down to Earth, and then they are returned to the scientific teams. So it's not as simple as just sending some samples to space. You really need to adjust the protocols that you are using. You need to work closely with the industry so they understand why you have certain requirements like temperatures or gas exchange. And they need to be very careful when designing the payload to ensure that it fits into whatever facility that it needs to fit. And currently what ESA is trying to do is to develop technology to enable this process to be a bit simpler. So we are focusing on developing standardized hardware that you can use many times. So rather than having for each experiment a different specialized hardware developed, we want to have standard hardware that is also maybe commercially available so that the scientists can practice their protocols in their lab without having to invest a lot of time and effort into trying to fit it into a specialized space container. And we are also working on technology to have direct analysis of samples while they are in orbit. So rather than having to bring down samples to Earth, which is costly and runs a risk of loss, we want to develop microscopes or molecular analyzers that can directly analyze the samples in space and just send the data back down. And I also wanted to talk to you a little bit about the ground and analog platforms that we have available through our directorate. So it's of course very interesting to send the projects into space and you get the most significant results out of those. However, you don't always need the space environment to get the results that you to test your hypotheses. And often you can use ground-based simulation facilities to check your protocol, prepare the experiment for space, or just to see whether there is any preliminary evidence to suggest that space even has an impact on your sample. So we have several ground and analog platforms across Europe, and I will talk to them about them in the next few slides. So, and I also want to point out we recently established an HRE, so Human and Robotic Exploration Biobank. So this is in collaboration with a Portuguese institute, the Gulbenkian Institute for Molecular Medicine. And the idea is to store all the samples stemming from our research that are left over or specifically collected for biobanking in this biobank, and then release research opportunities for other researchers to request these samples and analyze them. And hopefully we would then maximize the amount of use we get out of each sample and increase the scientific return we can do with our space and ground analogs. And this is a relatively new activity, but we have actually last week completed the first ingestion of samples from a study with something like 40,000 samples ingested. So this will continue to ramp up, and hopefully we will be able to release a research opportunity soon to distribute these samples to other scientists as well. So now onto the different platforms that we have. First of all, the parabolic flights. So this is a type of flight where the plane does a parabola, and during the parabola there is about 25 to 30 seconds of real microgravity experienced during that time. And it's actually the only non-space platform that allows human research to take place without having to have specialized trained astronauts, for example. So you can recruit volunteers to join on this plane to perform some research without having to go to space. And then we have also sounding rockets. So these are suborbital rockets that are providing around 6 to 9 minutes of real microgravity as well. We cannot send humans on those, but we can send small experiments on these rockets to check for effects of microgravity when you don't need a very long exposure to microgravity. Similarly, there is a drop tower in Bremen, where basically a payload gets dropped, and it manages to experience about several seconds of microgravity, 7 or 8 seconds. But for some research, this is enough to see the effect that they are looking for. So there was recently a project called UDROP looking at ion properties in frog oocytes. And they were able to use this platform to analyze the conductivity of that ion channel in microgravity. And then we have several ground-based facilities. We call them ground-based, but they're not related to, for example, parabolic flight. These are facilities such as large diameter centrifuges that can host humans, or random positioning machines, which can simulate microgravity, where you can put cell cultures in, for example. And I just wanted to highlight one study that made use of the loop facility, where essentially a person is suspended on bungee ropes, and that can simulate gravity levels on the moon and Mars. And they were doing their research to understand how movement changes between those different gravity levels, and how we might need to develop specialized countermeasures to ensure that when we send crew to Moon and Mars, they are prepared to move on those different gravity levels. Then we have the golden standard of microgravity physiological simulation called bed rest. This is essentially where subjects are placed on bed rest for many days. There's very long times, such as the 60-day bed rest study that we have recently done. And typically the subjects are inclined 6 degrees downwards. And it has been shown that this really simulates physiologically the effects of microgravity, and allows us to, again, study the physiological effects and develop countermeasures for these. So here you can actually see in this diagram a subject who is in a bed rest, but also performing a cycling activity, because we are trying to optimize the exercise routines that astronauts might need when they are going on a long-term mission. And similar to bed rest, there is the dry immersion platform. This is essentially when subjects are placed in a water bath. They're not obviously swimming, but they're placed on top of water. And this is a relatively new capability in Europe, so it's currently being verified as something to use to simulate microgravity environment. And there have been 3 studies, actually, and here I'm presenting 2, but there was a third one as well, when they've essentially found that some of the physiological effects that you would get in microgravity are experienced faster in the dry immersion model, whereas others are not. So this could be a good platform to use when studying very specific systems and trying to develop countermeasures for those. So going to space for a very long time also has an impact on psychology. So we have several platforms that look at the isolation and confinement aspect of long-term missions. So for example, in Germany, there is the NREHAB, which is a very highly controlled isolation platform that you can send subjects there, for example, for 100 days, which is what we are going to be doing, to study the psychological impact of being isolated for such a long period of time, but also other things such as environmental monitoring and the impact on the immune system of being placed in such an environment. And then we have very high fidelity isolation and confinement platform, Concordia. This is an Antarctic research station that is at an elevation of 3,000 meters. So subjects or scientists who are there experience hypoxic conditions, and they're isolated really for 1 year. And it's actually more difficult to evacuate somebody from there than it would be from the International Space Station. So it's really a high fidelity isolation and confinement platform. And there we also collaborate with PFRA to perform some human subject research on the scientists and researchers who are visiting the station to perform some other type of research. So just as an example, we are able to investigate psychological impacts of overwintering on such a station, but also tracking contamination of the environment and trying to translate this to a space application. And then lastly, we also want to study the impact of radiation, both on the physiological impacts, but also on materials impacts. You might know that radiation can impact electronic systems and cause problems, so it's really important to understand how those occur and try to mitigate them. So we have several accelerator facilities across Europe that we work with, where we're able to expose samples to specific controlled radiation beams to derive the impact and try to develop countermeasures. And one of the accelerators we work with is the GSI in Darmstadt, which has a galactic cosmic ray simulator, which, as far as I know, is the only one in Europe. And this one is really interesting to use, because where our understanding lacks is really from the deep space radiation impact on physiological systems. And then I just wanted to also highlight how you can get engaged with our program. So we have several ways or opportunities for researchers. One is to go for campaigns. So we release these so-called Announcement of Opportunity, or AOs, which are opened every 1 or 2 years. And these are to use specialized platforms like the International Space Station or maybe a lunar platform. And once proposals are submitted, they are peer-reviewed by external peer reviewers to check the scientific quality of the proposals, and then they are implemented. But it usually takes quite a long time because, as I mentioned before, you often have to develop specialized hardware to host samples or to fly to that destination. Then we have continuously open research announcements, or CORA. So, for example, the ground-based facilities and parabolic flights, drop tower, these are all CORA activities. So researchers can apply to make use of those platforms throughout the year. And here, again, the proposals are peer-reviewed externally, but the implementation of the projects is much faster than when trying to go for the International Space Station, for example, because the platforms are just more easily reachable than the space station. And what ESA covers in terms of the research for that is the access costs to the facilities, as well as the costs of building hardware necessary to implement the study. What we don't cover, however, is consumables and other costs of experiments or travel costs or funding the science team, essentially. This is normally done by the national agencies, which can then support the scientists, whereas we would support then the development of the hardware or the access to the platform. And just to briefly highlight what we currently have open and what will open. So as I mentioned, parabolic flights, drop tower, ground-based facilities, these are continuously open research announcements that you can apply for. I've put some links here in the slide, but essentially on OSIP, this ESA's Open Space Innovation Platform, these calls are listed there. And then we have specific AOs. So there is the Concordia platform, the Antarctic Isolation platform, and there will be an announcement of opportunity for that soon. And an isolation and confinement AO, if it occurs, will happen likely early next year. In terms of low Earth orbit, there will be an AO to make use of autonomous platforms. So as you might be aware, the lifetime of ISS is coming to an end, and there are many autonomous platforms, i.e. uncrewed platforms, that are being developed, and we will release the research opportunity to fly projects on those. And then for Mars, there may be this announcement of opportunity for the Zephyro, in case we go ahead with that or not. And then we have a continuously open research announcement called Topical Teams. This is not so much to implement research, but it's actually a collection of experts or scientists who's focused on a specific topic to try and either develop a roadmap or perform a preliminary protocol or write recommendations about that very specific topic. And this is continuously open. So if you are interested and you want to become part of an expert group, you can apply to become a member of a topical team throughout the year. And there is also funding available for that. It's not a lot, but it's enough to cover, for example, publication costs or organizing a symposium or workshop on the topic of interest. And that's actually the end of my slide deck. So thank you very much for listening. I hope it was informative, and I am open for questions.
Thank you very much, Christiane, for this very informative presentation. That was a lot of, I think, very useful information for anyone interested in making science and doing it with some kind of support from European Space Agency. I wanted to remind our audience about the possibility of asking questions to our speaker. Of course, you can do it directly on the chat on the YouTube, so you can ask your questions. And before I will move to the questions from this sector, I have my own, so I have to use the opportunity to ask it. So I wanted to ask you, Christian, about the moon, because we know that there are plans of coming back there and having the habitats or some kind of laboratories built there. And I wonder, do you as a biologist see any kind of particular advantage of having laboratories directly on the moon that wouldn't be achievable on other platforms used nowadays? So, for example, on the ISS or on the ground-based facilities you mentioned.
Yeah, that's a very interesting question. And as a biologist, I do think there is relevance to having a laboratory on the moon to answer some very specific questions. So, as I mentioned before, what we're lacking understanding in is the deep space environment impact on physiological systems. So, it would be great to have a research lab there where we could expose human samples without having to expose the humans themselves to study the impact of the radiation, but also the lunar dust. Because when we went to the moon a long time ago, 70 years ago or so, there was some studies, some reports that there was irritation in the mucosal parts of the astronauts that went there. And there has since been quite a heavy research line into the impact of lunar dust simulant on mucosal membranes. So that would be an interesting topic to study there as well. Additionally, especially for the astrobiology community, I guess it would be very interesting to be able to perform some exposure type biology experiments on the moon, also to get the interaction of radiation and potentially lunar dust. And lastly, I know for the plant community, it's also very interesting because there is a lot of interest to understand whether the regolith found on the moon is actually beneficial to grow certain plant species. And that could be an interesting domain to look into a bit more. And these environments you really cannot simulate on ISS or on the ground, especially the combination of partial gravity, radiation, and dust.
Yeah, so definitely a reason to go there, despite everything. Yeah, I think we can move to the questions from the audience because I see some. And the first one is, it's very difficult to find this information on the ESA website. What biology-related research teams or research groups are organized within the human and robotic exploration? So do you have some particular differentiation between different research teams, let's call them?
So in terms of HRE or a human research team in general, we don't do the research ourselves in-house. So I'm not in the lab anymore, unfortunately. But we work with the science community, so the researchers across Europe. And if you want to know who those researchers are, I would suggest to go to the space-related conferences like ELGRA, where a lot of them are present to network with them. But we also have an archive where we list all the experiments that have been done with us, and you can find then publications and contact details to those research teams. So that website is called HREDA, the HRE Data Archive. If you Google it, you should be able to find the portal to that, and you can essentially search the site to say astrobiology, for example, and it will list all the experiments we have done in that domain together with some information.
Yeah, that's a great tip, I think, to research that topic. So I think we can go to the second question. Assuming we manage the radiation problem, what are, in your opinion, the biggest challenges to address on future lunar or Martian bases?
It's a good question.
A lot of them.
A lot of challenges. I'm not sure which one would be the biggest. I think for Moon, it's less critical because actually the Moon is not that far away, so you can return relatively easily. But for Mars mission, what's really challenging is the lack of resupply possibility. So you need to really bring everything with you that you need if you want to send humans there. That includes food, medication for like a 3-year trip. And all those things weigh a lot of weight. And it's difficult to place a lot of weight on launchers to go very far. So optimizing the amount that you need to take with you and being able to produce things on the vehicle itself is something we are looking into and trying to countermeasure that challenge. But also especially for human psychology, the isolation, I think, would really play an important role because you are away for 3 years and it's not like you can just call your family very easily. When you reach a certain distance, there will be a time delay and it will likely have quite a big impact on the people going there.
Yeah, I think Concordia is a good place to show that complete enclosure and being far away with high risk to your life. This is, I think, the best stimulant for now that we have. And I think I see the last question from the audience, a very interesting one. So, what are ESA's plans for conducting experiments in orbit after the ISS deorbitation that we know that is coming?
Yeah, so as I mentioned briefly, we are working to release opportunities for using automated platforms. So you don't always need to send a human to understand biology in space. You can send tissue on chip models or organoids when you validate them on ground. But yeah, there are a lot of automated platforms up and coming that are likely to be launching in the next few years. So those will allow you to expose your samples for 2 months, for example, and if you're thinking about Space Rider. Yeah. Basically automated platforms, but there is also the commercial crewed missions that are in development. So the Americans have VAST and Axiom. In Europe, we are looking into Starlab, which are crewed vehicles that would basically replace the International Space Station. But we are still learning how to work with them, and we are setting up the rights access to those platforms so that we can make that available to the community as well.
Mm-hmm. So, speaking about the space experiments, still, what do you think is the biggest challenge or the biggest difference in designing the experiment for the space platform, such as ISS, for example, comparing to the ground-based facilities?
Well, in ground-based facilities, you can always go back to your lab incubator, or you have a bottle of ethanol that you can spray stuff and clean it. You don't have that in your space hardware, so you need to think about everything up front and ensure it all works completely as planned and is very well tested. So I think that's difference. And one challenge I foresee with using automated platforms is if you have to design your hardware different for each platform. And let's say you don't know which one you can access and you plan for one, but then that one doesn't work out, you'd have to completely redesign unless there is a standard hardware. Um, you'd have to redesign for another platform. So
Yeah. So
yeah,
it's more like a single shot for the space experiments. You don't have a chance to give it another try, right? Once it doesn't work, it
this
doesn't
is,
work.
yeah, that's one of the lessons learned we have from the time on ISS. Is that's a big weakness that the researchers cannot repeat their experiment. So that's why we're trying to solve this with building standardized hardware.
Hmm. That's a really interesting opportunity. I think that will sum up our talk today. Thank you, Christian, for your presentation. That was, as I said, very informative, and I think we all learned a lot about ESA plans and possibilities in ESA for making space biology related experiments. Mm, this is also the end of this part of Life and Space Days for now. But at 7 p.m., I wanted to invite you all to another talk with Sarah Ziegler, um, also organized within the Life and Space Days organized by Polish Astrobiological Society. Once again, thank you all for attention. Thank you, Christian, for being here with us and sharing your experience. And yeah, that's it from me. And see you on the other live. Thank you.